Hello and welcome to this first lecture in a series of 5 where we're going to think about how we can use oxygen isotopes from carbonates in lake sediment in order to reconstruct past environmental change. So in this first lecture we're going to provide the context on what isotopes are, what isotope fractionation is. So I'm Jonathan Dean, I'm a lecturer in physical geography at the University of Hull in the United Kingdom. So I'll be doing some of the lectures, and then Matt Finkenbinder from Wilkes University in the United States will be doing other lectures in this series of 5. So yeah, firstly, to start off and think about what isotopes are. So this is what you would find if you looked up oxygen on the periodic table. So oxygen is defined by having 8 protons. That's what the atomic number is. Okay. However, you get different types or different isotopes of the same element. So isotopes have the same number of protons, but a different number of neutrons from each other. So for example, with oxygen, which is what we're focusing on in these lectures, most oxygen on Earth, 99.76%, is what we call oxygen 16. So this number here is the number of protons plus the number of neutrons. So remember, all oxygen has 8 protons. Oxygen 16 has 8 protons and 8 neutrons. Oxygen 17, so you can see hardly any of the oxygen on Earth is oxygen 17. This has 8 protons and 9 neutrons. And oxygen 18 has 8 protons and 10 neutrons. You can see 0.2% of oxygen on Earth is this one. So let's just show that here. So we've got oxygen 16, oxygen 18, same number of protons, oxygen 18 has 2 more neutrons. So just to clarify what stable isotopes means, because you might see this when you're reading in the literature, stable isotopes are just isotopes that do not radioactively decay. Okay, so these are oxygen isotopes, they're stable isotopes, they do not radioactively decay, whereas something like carbon-14, radiocarbon, that does radioactively decay. Okay, so before we start to consider how we can use stable isotopes to reconstruct past environmental changes, that's going to be coming up in the next lectures. Let's think about the basics first. So we're looking at isotope ratios, a change in the proportion of one isotope of an element to another. We're looking at, say, the ratio of oxygen 18 to oxygen 16. So isotope ratio, isotope ratios you would usually write it like this. So delta 18O, so this is the Greek delta symbol. So delta 18O is literally just shorthand for the ratio of 18O to 16O. Okay. And isotope ratio is usually measured in per mil. So, you know, percent is out of 100, this is out of 1,000. So you can see the similarity in the symbol. So it's measured in per mil and it's measured relative to a standard. So if you're measuring, for example, water, you look at the ratio of oxygen 18 to oxygen 16 in your sample, and you compare this to the oxygen isotope ratio of a standard, and it's given in per mil. So the standard for water is Vienna Standard Mean Ocean Water, and that has an 18O/16O ratio of 2005.2 ppm, parts per million on average, roughly. Okay, so for every million, so ignore oxygen 17, for every million particles of oxygen 18 and oxygen 16, 2005.2 of those will be oxygen 18 out of the million, and the rest will be oxygen 16. Okay, so then if you measure your sample and you've got your delta 18O value, and the value is you've looked at the ratio in your sample, you've done that equation, you compared it to the ratio in the standard. If your delta 18O is 0, that means it has the same oxygen isotope composition as the standard, because you've done that equation, you've compared it to the standard. So if it's 0 per mil, that means you have the same 18O/16O ratio as is in the standard, in this case VNS standard mean ocean water. If you have positive values above 0, that means you've got less 60No, more 80No than the standard. And if you have negative values below 0, that means you've got more 60No, less 18O than the standard. So we're not going to go into this in detail, but just to point out, you measure these ratios on something called a mass spectrometer. So you put your sample in at the beginning, and it goes through a magnet, and because of the different masses of the isotopes, and this is CO2 being put in here, so what we'd be measuring at the end would be, you'd be able to calculate the carbon and oxygen isotope ratios in this case. But if you've got a molecule of CO2 which has heavy carbon, heavy oxygen in, it will take longer to go around the corner than if you have light carbon, light oxygen isotopes that will go around the corner quicker, to simplify that very much. Okay, so then you're measuring in these things called ion detectors at the end, these these different masses, and yeah, from that you can, in this case here, you'd be able to do some maths and you can calculate what the carbon isotope ratio is, what the oxygen isotope ratio is. So what can we measure delta 18O, the oxygen isotope ratio, on? Well, anything that has oxygen in. So, for example, this could be ice from glaciers, it could be on trees, it could be on lake sediments. So let's take lake sediments as an example to go into a bit more detail on. So you go to a lake, you drill sediment, you drill into the sediment at the bottom of the lake. So you're going from the current day lake bed at the top, so sediment formed in the present day, and you're looking at the oxygen isotope ratio on all these different layers going back through time. And that allows you to reconstruct some aspects of the environment. And we'll think about what those aspects are later on in the series of lectures. But basically, yeah, you're analysing the oxygen isotope ratio and looking at how that ratio changes as you go back through time. So this change in the ratio is called isotopic fractionation. So this is because these isotopes, so for example, oxygen 16, oxygen 18, they have the same number of protons. So chemically, they pretty much behave the same. But in terms of physical processes, because they have different masses, they do act slightly differently. For example, in evaporation and condensation, physical processes. So it takes more energy to move a heavy atom into a more disordered state. So for example, liquid to gas evaporation. So if you've got your water molecule and it has 16O as the oxygen, that will be easier to evaporate than your water molecule if the oxygen is oxygen 18, because this one will be heavier. So it's harder to evaporate than if you had the water of oxygen 16 in, which is lighter, easier to evaporate. Conversely, if you're going from gas to liquid, so condensation, it's easier to condense out water if it's got oxygen 18 in, compared to if it's water of oxygen 16 in. So yeah, water that has oxygen 16 in is preferentially evaporated. It's slightly easier to evaporate than water of oxygen 18 in. So yeah, you will get evaporation of water with oxygen that has oxygen 18 in. However, preferentially, you will get evaporation of water that has oxygen 16 in, just because it's easier for that to be evaporated. Whereas conversely, in the cloud, when you're condensing out and forming precipitation, water with oxygen 18 in is preferentially removed over water with oxygen 16 in. So this is why we might get changes in the oxygen isotope ratio in the water. If we have lots of evaporation, you're going to end up with lots of water of oxygen 16 in has been evaporated away. And if that is stored somewhere, as like on a glacier, isn't returned to the ocean, then what you're going to end up with is a change in the oxygen isotope ratio of the water, because you end up with loads of oxygen 18 left in the water and loads of option 16 has been evaporated away. So you might get a change in the ratio oxygen isotope composition of the water in that example. So yeah, as things like temperature, sources of rainfall, amount of rainfall, evaporation, those other things that we'll talk about later, as these things change, this causes a change in the isotope ratio, isotopic fractionation. So if you have your lake sediment core or a tree or whatever that's going back through time, and you look at the ratio, oxygen isotope ratio, and how that changes back through time, that could allow you to reconstruct something like amount of evaporation, amount of precipitation, something, temperature might be able to reconstruct something that changes as you go back through time. So yeah, biological, geological material, something that's accumulating material over time. You look at the oxygen isotope ratios back through time, that could allow you to reconstruct some aspect of environmental change. So this is an example of a study that I've been involved in. This is reconstructing how, in this case, precipitation evaporation ratio, so climate change between wet and dry, how that changed going back through time. So this is a sediment core taken from a lake in Turkey, and this is the oxygen isotope ratio, so higher values upwards, lower values going downwards. So what we were able to show in this lake, the oxygen isotope composition, the oxygen isotope ratio of the carbonate in the lake sediments, that varies depending on the precipitation evaporation ratio. So in other lakes, it might vary more due to temperature, whereas in this lake, it varied due to precipitation evaporation. We were able to demonstrate that was the case. So then this oxygen isotope ratio changed back through time. We are then able to show that higher values means it was drier, lower values means it was wetter. So we've got quite dry conditions around 4,000 years ago, and we've got quite wet conditions around 10,000 years ago, and changes between those times. So yeah, we're from this oxygen isotope ratio of the carbonate in these lake sediments, we were able to reconstruct how the precipitation evaporation ratio, wet dry climate, how that changed going back through time. So in these videos, we're concentrating on oxygen isotopes because there's enough to say about those on their own. But just to point out, there are other isotope ratios that you can produce, and they can be useful for reconstructing past environmental change, paleoenvironmental change as well. So you've got the carbon isotope ratio, the ratio of carbon-13 to carbon-12. You've got the hydrogen isotope ratio, the ratio of deuterium, or hydrogen-2, to hydrogen with just one proton. You can use those. These are also useful isotope ratios for reconstructing past environmental change. Okay, so that's the end of the first of these 5 lectures. So here are some summary questions. So yeah, pause the video here, have a look through these summary questions. Hopefully you can answer them. If you can't answer them, go back to the relevant slides and listen again to what I said, and hopefully you'll be able to answer them then. Thank you very much.